discuss selected topics of physics, stage number 3, which is called electricity and magnetism. As you know, the study and knowledge of electric phenomena has resulted into technological advances pretty relevant for development and growth of humanity. Nowadays, we are all surrounded by many different types of electric devices, such as lamps, motors, cell phones, computers, TVs, etc. So that's why it's important to understand the electricity and its applications. In this video, you will learn electric charge, conductors and insulators, Coulomb's law, electric field, electric potential energy, electric potential difference, electric current, electric resistance, Ohm's law, electric circuits, and magnetism. Well, so let's begin!
During this video, we are going to be talking about electricity and magnetism. Once again, here is the content of the stage. First, we must understand that electric interactions happen because of the electric charge, which, just like a mass, is a fundamental quantity that cannot be described in terms of simpler elements. In order to understand better what electricity is, we are going to analyze electrostatics, which studies electric charges at rest. All matter is made up of atoms, which in turn are made up of elemental particles like electrons, protons, and neutrons. Neutrons are electrically neutral because they have no electric charge. We say electrons have negative charge and protons positive charge. A normal atom is neutral because it has the same number of protons as electrons. Anyway, if the atom gains electrons, then it will have negative charge because the number of electrons is greater than the number of protons. On the other hand, when it loses electrons, we will consider the charge as positive because there will be more protons than electrons. The behavior of electric charges or bodies charged electrically is established in the fundamental law of electric charges, also known as the law of charge force, which says, like charges repel and opposite charges attract. There is a principle named as the principle for the conservation of electric charge, and it establishes that in an isolated system, the amount of electric energy is preserved. That is to say, if one body loses electrons, another body gains them. Materials can be classified into conductors or insulators depending on the movement of the charge when it's placed on top of them. When a charge is placed on top of a conductor, the charge is distributed over the entire surface because these materials have free electrons inside. For example, metals as copper, silver, gold, steel, tin, and bronze are very nice conductors. But when a charge is placed on top of an insulator, the charge will remain in the same place. The most common insulators are the wood, cloth, glass, paper, plastics, etc. How can we electrify a body? Actually, there are 3 methods to electrify a body. It could be by using friction, that can be seen when a body is rubbed with another. We can also electrify a body by contact, when a charged body touches another, and finally by induction, when an electrified body gets closer to another one. What is the unit used to measure the electric charge? It is called coulomb, and it's represented with the capital letter C. It is defined as the unit of charge such that if a charge could be placed 1 meter away from another same charge in vacuum, there would be acting between them a force of 9,000 million newtons. Thus, 1 coulomb equals 6.24 times 10 to the 18 times the electric charge of the electron. And as you can see, 1 coulomb is a pretty big quantity of charge, so that's why it's common to use the submultiples. For example, the millicoulomb, the microcoulomb, or the nanocoulomb, whose equivalences can be found in this table. The Coulomb's law. This law establishes that the magnitude of the electric force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance that separates them. This means that the greater the quantity of the charge, the greater will get the force. But the greater the separation, the lesser the force. So, this law can be represented with the following equation, where K is the constant of proportionality, Q1 is the charge number 1, Q2 corresponds to the charge number 2, and R is the separation distance. Now, we are going to solve the example number 3.1 from page 99 in your textbook, and it says, a positive charge of 6 times 10 to the negative 6 coulomb is 0.03 meters away from a second positive charge of 3 times 10 to the negative 6 coulomb. Letter A. Calculate the force between the charges. Letter B. What would be the force if the second charge were negative? Well, first, let's write down the data. We are going to use the Coulomb's law formula. Now, let's substitute the variables with data and help yourself with the calculator to find the result. You can see that the force equals 180 newtons. Don't forget to write the units. This force will be of repulsion because the charges have the same sign. For letter B, we have exactly the same values, so the magnitude of the force would be exactly the same, that is to say, 180 newtons. The only difference is that the force would be of attraction, because the signs are opposite. For a better comprehension of this topic, I invite you to resolve the activity you can see on the screen. Right now, let's talk about the electric field. A charge produces an electric field around it, which is a region of the space where an electric charge experiences an electric force. The electric field is a vectorial quantity, that is to say, it has magnitude and direction. The magnitude of the electric field, represented with letter E at any point, in terms of the force experienced by a small positive charge when it's placed at that point, is equivalent to the force per unit of charge, that is to say, E equals F divided by Q, and its units are newtons per coulomb. The direction of the electric field at any point corresponds to the direction of the movement of the positive test charge exerted on this point. It can be shown that the greater the charge exerted in the electric field, the greater the magnitude of the field, and in turn, the greater the distance between the positive test charge and the Q charge, the lesser the exerted force. Let's use the Coulomb's law and now write it this way. Then, we are going to use the equation of the magnitude of the electric field and substitute F. Next, we may cancel Q0, and we are going to obtain an equation that depends only on the charge and the square of the distance. Let's see together the example 3.3 from page 103. Calculate the intensity of an electric field at a distance of 50 centimeters from a charge of 4 microcoulombs. So, write down the data, but be careful with the units. Let's use the formula and replace variables with numbers. Use your calculator to find the solution and write down the correct answer in newtons per coulomb. As a recommendation, try to solve this activity before you continue. This time, we are going to learn what electric potential energy is. I'm pretty sure you remember the concept of gravitational potential energy. When a work is done on an object against the gravitational field, so it can be lifted certain height, this object will accumulate gravitational potential energy. If the object is released, the potential energy will start to become into kinetic energy, and this will move the object downwards in the same direction as the Earth's gravitational field. In the same way, we can explain what electric potential energy is. You may know that between a positive and a negative plate, there is an electric field toward the negative plate. So, obviously, if a test charge is placed between these plates, this will move toward the field's direction. Now, let's suppose you want to move exactly the same charge against the electric field from a point A to a point B. So a work has to be done, and some of the energy will be accumulated in form of electric potential energy. Then, when the charge is released, the potential energy becomes into kinetic energy, and the charge is moved toward the field's direction. With this information, we can define the electric potential energy as the work done on a test charge to move it from one point A to one point B against the electric field. The work is expressed as W equals force times displacement, and we already know that the electric field equals the force divided by the charge, from which equation we can isolate F, and we have F equals E times Q. If we replace EQ in the work formula, we can say the electric potential energy equals the magnitude of the electric field times the charge times the displacement. And because this is a type of energy, it must be expressed in joules. The difference of electric potential, also known as voltage, is defined as the necessary work to move a unit of a test charge from a point A to a point B against the electric field, that is to say, the work done per unit of the test charge. In other words, we can take the electric potential energy formula and divide it by Q. Simplifying, we have that the voltage is equal to the magnitude of the electric field times the displacement. The voltage is measured in volts. For a better comprehension of this topic, you may solve this activity. Another important quantity is the electric current, which could be defined easily as the flow of electrons through a conductor. It is represented with letter I, and its equation is I equals Q divided by T. The units for electric current is called ampere. An ampere could be defined as the flow of 1 coulomb per second at a determined point of an electrical conductor. Please try to solve this activity for a better understanding. Not all materials can conduct the electricity in the same way. It depends on the electric resistance, which could be defined as the opposition to the passage of the electric current. The fundamental unit is the ohm, represented by the Greek capital letter omega. Actually, the electric resistance depends on 4 factors: the specific resistance of each material, the temperature, the length of the conductor, and the cross-sectional area. I will invite you to solve this activity. An electric circuit is every closed circuit in which charges move from a voltage source, which is pumping the charges through a conductor, to a device that transforms the electric energy into another type of energy: kinetic, light, heat, etc. There are 2 main kinds of circuits: series circuit and parallel circuit. In a series circuit, the electric resistances are connected one after another. The voltage of the source is equal to the sum of the voltage of each resistance. The electric current in the resistance is the same for all. This circuit can be simplified and then be represented with an equivalent resistance. The equivalent resistance is equal to the sum of all electric resistances in the circuit. let's suppose I have 3 light bulbs in a series circuit. So, if suddenly I disconnected one of the light bulbs, the other 2 ones will turn off because the circuit will be open and the current could not flow anymore. Is this kind of circuit familiar to you? Well, now it's time to talk about the parallel circuit. In a parallel circuit, 2 or more resistances are connected directly to the same source or point in the circuit. The voltage is the same for each resistance, and the total current of the circuit is equal to the sum of the currents of each resistance. This kind of circuit can be simplified too by obtaining the equivalent resistance, but first you have to obtain the reciprocal. The reciprocal of the equivalent resistance is equal to the sum of the reciprocal of each resistance. At the end, you need to calculate the reciprocal of the reciprocal in order to find the equivalent resistance. So, now, let's suppose I have 3 light bulbs connected again, but this time in a parallel circuit. If suddenly I disconnected one of the light bulbs, the rest of them still will be on, because the circuit does not open to them. And this, just like the lights of a house. The Ohm's law can be used to establish the behavior of the voltage, the current, and the resistance in the circuit. And it says, if the voltage of a circuit is increased, then the intensity of the electric current increases too. If the resistance of the circuit is increased, then the electric current is decreased. The current cannot be expressed in amperes, the voltage in volts, and the resistance must be expressed in ohms. For this activity, you will read examples 3.10, 3.11, and 3.12 from page 120, and then try to solve the problems 11 and 12 from page 134. Now it's time to talk about the last topic of the stage, the magnetism. The magnetism is a property of some substances to attract other substances such as air. A magnet is a body that possesses magnetism. The compass, for example, is a magnet with the form of a needle that can rotate and will always point the Earth's poles. It has been used by navigators since ancient times. A magnet can have different properties. Property number 1. A magnet will always have 2 poles, a north pole and a south pole. They received this name because if a magnet with a bar form was suspended with a string, this will point the Earth's poles, but the north pole of the magnet will always point the Earth's geographic south pole. Number 2. A magnet responds to the fundamental law of magnetism. Like poles repel and opposite poles attract. Number 3. The poles of magnet cannot be separated. If you try to split a magnet in order to separate the poles, you will obtain 2 small magnets instead. The magnets produce a magnetic field in the space that surrounds them. The force lines of the field are emitted from the North Pole to the South Pole. In 1820, the Danish physicist Hans Christian Ørsted demonstrated that electric current produces a magnetic field. This fact was the beginning of the electromagnetism. Finally, it would be nice if you could answer the self-assessment from page 238. This way, you could measure your knowledge.
Thank you for watching and paying attention. That was the stage content. I hope you like it. Don't forget to upload your learning evidence in Nexus, in which you have to make an experimental prototype where you must apply all the knowledge you have just acquired. If you have questions, get closer to your teacher. See you later.